Welcome back to ECE 441A, 541A. Hopefully it comes as no surprise that homework number 4 is due today. If you turned in a hard copy for homework number 3, it's in the folder. If you turned it in online in D2L, you'll just have to look at your comments on D2L with your soft copy, and hopefully we'll get that interchange of information flowing smoothly. Homework 5, I think I've actually assigned that already, and that's due Wednesday before the exam, which is a week from today. So a lot of things are happening. Lab number 2 is now available. I apologize. I'll try to get your lab number 1s commented on this weekend. So you maybe can start looking at the demo this weekend or looking at what's needed. But essentially that one is you're moving the closed loop poles by full state feedback. You're feeding back position information, you're feeding back velocity information, and that now allows you arbitrary movement of your poles in the complex S-plane. And you should, after what we've talked about with design specifications, understand where those pole locations, how those impact your performance in the system, how they impact settling time, percent overshoot, peak time, etc. And you'll need to become an expert on those issues for exam number 2. Again, that's a week from today, and hopefully we'll have just a few more players on the field when we have our exam on Friday versus today. But I'm guessing everyone is at home watching, maybe, hopefully. We'll start today with a design question, which we will actually circle back around and treat that a little bit more formally later on. I don't know if we will get to the last point today, but today's class is now moving on from design specifications and steady state error to stability. How can we actually determine stability of a polynomial without using your calculator, without factoring it? Do we have to factor it? And the Routh-Hurwitz produces an array of numbers, which we can now look at the leftmost column in that array after we've generated it and determine information about the locations, relative locations of those poles. Are they in the right half plane? How many are in the right half plane? Are there some on the imaginary axis, or are they all in the left half plane? Those are the kinds of questions we will be able to answer. We won't be able to say precisely where they are located, but we will be able to talk about right half plane, imaginary axis, and left half plane by performing this Routh-Hurwitz stability criteria. It's really 2 parts. There's a Hurwitz test, which is a necessary test, but it's not sufficient. If the test is not passed, then you know that the system is unstable. You may or may want to continue. It depends on what the question is. If it passes the test, then you still don't know enough information to claim whether or not your system is actually stable. And that's when we have to produce the Routh array, which is this matrix-looking object, but it's just an array of numbers, and we will concentrate on what's happening in the left column of that array of numbers. We'll go through some examples, and then we'll talk about how to do that by adjusting a parameter. Here's a question that helps motivate this idea, and this is for you now to try to determine. Can you find a value or values or a range on K? This is now, let's say, a knob on your system. You're adjusting K, and you want to know, can I adjust the gain K to make this system stable? The system nominally is unstable, the way I've represented this system in a block diagram. It has a pole at +1. We have a controller that we're putting in at -2, and we want to adjust the gain K. Is there a value, or are there values, or is there a range of K to produce a stable system? Question is, can you make it 0? Figure it out. See if you can get an answer. And you might answer your own question. What happens if you do make it 0? Pardon? This is a quiz. I know, I didn't clarify, but this is now, you're working on your own to try to find this K. Next Friday, I'll really get on to you if you start talking and asking questions on the exam. But today, that's okay. You're just waiting patiently for everyone to finish. Who has an answer? Ouch. Okay, give you a little bit more time. And you can now work together if you want. If you want to talk to a neighbor, see how they were moving or approaching the problem. Was it clear what was being asked? Let's now talk about this. Now we are trying to adjust a parameter, a gain parameter, to see if we can stabilize the system. And in a few weeks, this problem will be trivial. And actually, by the exam in a week, you should be able to solve this using the Routh-Hurwitz criteria. This is now trying to motivate, and this one is not as significant or complex as what it could be, and you could still solve a more complex problem with the Routh-Hurwitz criterion. How did we approach this problem? What's involved if we're trying to get the system to be stable? Okay, so now we need to find the poles of the transfer function, and the transfer function that we're after is which transfer function? The open loop, the product of those two, the closed loop. We need the closed loop system to be stable. We now need to, let's say, form the product or the cascade combination of our controller and plant or system. That's now our G, and now we can close the loop. That's G over 1 plus G. If we do that, if we now look at the closed loop transfer function, that's now this G over 1 plus G, where G is this K, S plus 2, S minus 1. Is that making sense? Then if we do that algebra, we end up with K over S plus 2, S minus 1 plus K. There I've obtained a common denominator in the numerator and denominator. That then cancels, and now I'm left with just a ratio of polynomials, the numerator polynomial and the denominator polynomial. If we then say, let's concentrate on the stability of this system, then for stability, we need to look at the denominator polynomial. And that's now this S plus 2, S minus 1 plus K. Or that's an S squared plus 2S minus S plus S minus 2 plus K. Did some of you get that far? And then maybe you didn't know where to go from there? That's what we want to talk about today. We want to talk about how do we pick these coefficients in a polynomial to at least stabilize the system. That's what we want to do, and we are going to actually learn. Did anyone just pick a K and say, let me pick a K and see if it stabilizes the system? That's one approach, right? You could just start saying, let me iterate, let me try to find some Ks that might make this stable. If you picked a K bigger than 2, you're going to be in good shape. That's actually the range. K needs to be bigger than 2 to stabilize this. What we are going to learn using the Routh-Hurwitz stability criterion, that in fact for a second order polynomial, the Hurwitz test actually becomes necessary and sufficient. And what we will learn is that a monic, is this polynomial monic? It is, because the leading power of the highest power is 1. S squared's coefficient is 1. A monic second order polynomial is stable if and only if the roots of the polynomial are in the left half plane. But for this particular second order monic, all we have to know is if those coefficients of the S and the constant coefficient, if those are present, that means they're there, and they're positive. So I always go present and positive. So those are now present and positive. If and only if it's two coefficients are present and positive. By that, I mean if we start with this S squared plus A1S plus A sub 0, we are now saying we want A1 to be positive and we want A sub 0 to be positive. If that's the case, then that polynomial will have stable roots. The roots of that polynomial will all have a negative real part, and that's what we want for stability. In this case, A1 in our example was 1. That's fine, wasn't it? The leading coefficient here was just a 1 on that. I'm sorry, the coefficient of the s power of the polynomial, and the s to the 0 coefficient, a sub 0, is minus 2 plus k. We need that to be bigger than 0. There's our condition for that system to be stable. We want to turn that knob on our k to be bigger than 2. It's not equal to 2, because if it was equal to 2, then we would actually have a pole right on the imaginary axis, and I could kick that with a step and cause the output to go unbounded. So it would be marginally stable with k equal to 2. We want to get both roots into the left half plane. So if you got 2, you're right there on the cusp of the right answer. I would maybe take off 24 out of 25, but at least you would get 1 point for that k equal 2. Everyone else would get 0 if they didn't get that. No, I'm kind of being facetious. But question? Now, it really, the question was, how complicated, I think, are these expressions going to be that involve k? K could appear in more than one coefficient, and the Routh-Hurwitz test will allow us to figure out, are there ranges or values or ways of selecting k that will produce a stable closed-loop system. If our k actually canceled the s coefficient, then what would we say? Let's say that s coefficient is 0. Now we have s squared plus, let's say, a positive number. S squared plus 2. What are the roots of s squared plus 2? Take the 2 on the other side. We have s squared is minus 2. Now plus and minus the square root of 2. We're right on the imaginary axis. So we have an oscillator. If somebody canceled, or if we had that coefficient of the s term, vanishing. If that was gone, then we wouldn't have a stable system. We would have an oscillator. We would have our closed loop poles on the imaginary axis. Now, I hope that now gives you a better feel for why we are talking about what we're talking about, which is stability, and how to find that by maybe adjusting parameters, or simply looking at these coefficients of our polynomial and saying, is it stable? Do I have poles in the right half plane? Do I have poles on the imaginary axis? Let's now look at this topic called Routh-Hurwitz stability. Now, I think we all know if we want a stable system, we know what that implies relative to where our denominator roots need to be, or where the poles of our closed loop system need to be. We want our poles in the left half S-plane. And I might actually just abbreviate that in the LHP. As long as the denominator roots are in the left half plane, we have a stable system. And the denominator is of our closed loop system. What we are wanting to do today is actually learn a technique that avoids having to factor a polynomial. We want a method for determining pole locations without having to factor the denominator polynomial d of s, where we have a system, let's say a closed loop system, that we are parameterizing by a numerator polynomial n of s and a denominator polynomial d of s. This is now a ratio of polynomials that is representing our closed loop system. We want to look at d of s without having to factor that or plug it into our calculator. Can we now assess where those roots of d of s are located? And this test, or criterion, the Routh-Hurwitz criterion, is based actually on algebraic tests on the coefficients of the denominator polynomial. We're now looking at the roots of d of s, and we'll find those by looking at d of s equal to 0. Let's now just define a generic polynomial, and I might call that a delta of s, I might call it a q of s, but let's agree that that's now a to the n, s to the n, so we're not requiring it to be monic necessarily, plus a sub n minus 1, s to the n minus 1, etc., down to a1s plus a sub 0. Each of the subscripts on a then immediately connects that with the power of s. A sub 0 is the s to the 0 term or coefficient. A sub 1 is the coefficient on s. This is the Routh-Hurwitz test, so we break it up actually into two pieces. First, we'll talk about Hurwitz. The Hurwitz test is as follows. This is a simple test to decide if the system is in fact unstable. And on a lot of the exams, I'm going to have you doing more than just checking stability or instability. I'm going to maybe ask you where are these roots located without using your calculator, now that you've gone out and spent $200 on a calculator. Here's the Hurwitz test. And I said above it was a simple test. The test says if you look at this polynomial, are all of the coefficients present? That means, are they there? Do they appear? If any of them are 0, you've already violated the Hurwitz test. But the first step is all coefficients are present. All of the a sub j's have to be there. They can be 1, they can be whatever, but they have to be there. And then the second piece of this test is all of the coefficients need to be positive. That's the Hurwitz test, and that's pretty simple. You can do that by inspection. You can just look at the coefficients. Are they all there? Oh, I'm missing the s cubed coefficient because s cubed isn't in my polynomial. That now doesn't satisfy the Hurwitz test. That polynomial is now unstable. If that's all Tharp needs, I'm done. Oh, they're all there. Oh, one's negative. It's unstable. 3 are negative. It's unstable. I don't have to go any further if that's the case, unless the question asks for more. Now, these conditions as I said before, are actually only necessary conditions for stability. Now you put your math hat on and you go, what in the world does that mean? Well, you can make basically one comment or statement by looking at this Hurwitz test. If this polynomial, delta of s, fails the Hurwitz test, so you're missing a coefficient or coefficients, or one or more are negative. If delta of s fails the test, then you can conclude that the system is in fact unstable. However, if this polynomial passes the Hurwitz test, that means all of the coefficients are there, they're all positive. What can you conclude? Nothing yet. So we need more information. The more information that we are going to obtain is coming from the second name in our criterion. The Routh is going to give us that, and that's the Routh array. We are going to now build up this array called the Routh array, and that's going to give us this additional information that we need. Let's now talk a little bit in general about the procedure associated with this Routh array. First, we need to build up the array. So I'm going to say the first step is to construct this array of numbers. Once you've built this array of numbers, you're going to actually have three different possibilities that you could have discovered in the process of building up or constructing this Routh array. First possibility, or the A possibility, is all of the, so you're going to have this array of numbers, and it's not square. It's going to sort of be in the upper left hand off. It's all kind of, it's not upper triangular because now we're going above the anti-diagonal. This will make more sense in a minute. But if all the left column entries, we will have a full left column of numbers, all left column entries in the array are non-zero. So now we've built up this Routh array, and we look at the left column, and we have all of those elements in the left column. They're there. They may not all be positive or negative. What we will do now is we will actually count, after we've built the Routh array, we count the number of sign changes in that left column. We just step down the column from top to bottom, and we say how many sign changes did we encounter or experience in going from the top row down to the bottom entry or bottom element. We then use that number. This number actually tells us the roots of our original polynomial with positive real parts. Let's just look at a basic example. Let's say that you've built the Routh array and the left column has a positive number, a minus number, or a negative number, and a positive number. That's in the left column. These are the left column elements. Now, another challenging task, how many sign changes are there in that collection of entries? 2. Positive to positive, no sign change. So I'm going from the top. Positive to minus, 1 sign change. Minus to plus, another sign change. So this simply means we take this column of elements, we look at how many sign changes. Here we have 2 sign changes. And that now says, therefore, we have 2 roots in the right half plane. That's the easy case. That's the easy possibility case. If we, in the process of generating the Routh array, all of those elements in the left column are there, then we simply count the number of sign changes, and that tells us how many roots of our original polynomial were in the right half plane. Possibility B. Here, let's say that we have a left column element in the array is 0, but if we looked in that same row where that entry is 0 in the left column, there's some non-zero entries to the right of that 0 element in the left column. That's what I'm trying to say here. With non-zero elements elsewhere in that row, then we can't even continue with our Routh array construction. We have to do something. And what we do is we now replace that 0 element in the left column with an epsilon. And then use that epsilon. Now we have a variable epsilon in the remainder of our construction of the Routh array. We replace the 0 element with a positive epsilon. We build up our array, and after we finish the construction of the array, we count the sign changes, again in the left column. As this parameter epsilon goes to 0. So now we let epsilon go to 0, and whatever that results in, maybe we had an epsilon minus 6. We let epsilon go to 0, what's that element going to become in terms of its sign? Epsilon minus 6. It's going to be negative, isn't it, as epsilon goes to 0. So now you would have a negative sign in that particular row of the left column, and you would incorporate that when you're counting sign changes. Now, once you've counted the sign changes, you can use the same rule that we had before. The number of sign changes in the leftmost column of this newly completed Routh array is going to equal the number of roots with positive real parts. That's the second possibility. The third question? So now the question was, and hopefully this will become a little bit more clear, I'm just trying to give you the rules now. but you will replace that leading epsilon, or that 1 0 element, with epsilon. As you're going on through the construction, maybe another entry in that table or array becomes epsilon minus 6, not the one that we just put in. So this is a subsequent row entry. On the third possibility, suppose now we find that one complete row in the construction of the Routh array is all 0, not just the leftmost entry. This is now the third possibility. We have an all 0 row. If that's the case, what we do is we replace, and I'm not going to write it again, the all 0 row. We replace the all 0 row, and this is going to really be interesting, but it will make sense as we go, with the differentiated auxiliary equation. I haven't even defined half of this stuff, but it will become clear. We have an all 0 row. We now find an auxiliary equation, and that's just from the row above the all 0 row. We differentiate that auxiliary equation with respect to S, and that result gets placed into that all 0 row. And then we continue building our Routh array, and again, we simply can count the sign changes. And we have the number of sign changes equaling the number of roots with positive real parts. And now let me just say that the auxiliary equation in that third possibility is created from the row in the Routh array immediately above the all 0 row. Now that we know what the possibilities might be, and maybe it's still not very clear, let's build this silly Routh array. Let's construct it, and then we'll start to be able to see where these different possibilities might arise. Here is now the technique for creating the Routh array. So now we're going to do some construction. Did everybody bring their hard hats? Or I guess we're in ECE, at least your closed-toed shoes, apparently, if you're on the third floor, right? Make sure you don't have sandals on. We don't want solder dripping on our toes, hot solder. Construction. Here is our polynomial, d of s. It's, again, this a sub n, s to the n, plus a sub n minus 1, s to the n minus 1, plus a sub 1s, plus a sub 0. We're not accountants, but we're going to actually do some bookkeeping. You may all be accountants for all I know, but here is, I'm just going to, you may not see this in textbooks when they're building the Routh array, but I like to have a column that actually tells me where I'm located. Here's the s to the n row. Here's the s to the n minus 1 row. Here's the s to the n minus 2 row. Here's the s to the n minus 3 row. And it just keeps going and going until we run out of powers of s, and we will get s to the 1, and then we will get s to the 0. Once we've filled up the s to the 0 row, we're done. Now, to build this array, we start from the top. This is just bookkeeping, this leftmost notation, s to the n, s to the n minus 1. Starting with this polynomial, we simply find the highest power of s, and that tells us how to begin. We take the coefficient of the leading power, or the highest powered s, and we place it right here, a sub n. Then we skip a power of s, and the next entry in our Routh array is now the a sub n minus 2 coefficient. And we now just have that pattern. The next entry is a sub n minus 4, a sub n minus 6. And if we're dealing with a 13th order polynomial, we're going to have a lot of entries in that top row. Just preparing you for Friday, okay, for a 13th order polynomial. But we now have used every other coefficient, and now if some are 0, that's where you get stumped. You need to make sure that you jump over or don't jump over coefficients that might be 0. If you start with a 4th order polynomial, you have a sub 4, then you have a sub 2, then you have a sub 0, and that top row is done. Now the bottom, or the second row in the Routh array picks up the other coefficients in that polynomial. Right, so if you have a 0 coefficient, it doesn't pass the Hurwitz test, but like I said before, I may not let you escape that easily on the test or homework. I may have you say, okay, so it's not stable. Tell me about the polynomial. How many roots are in the right half plane, how many are on the imaginary axis, and how many are on the left half plane? Because I want you to build the Routh array. Yes, so if you're just asking for stability and you have a 0 coefficient, you could say, it's not stable, I need to do something. But now the second row is a sub n minus 1, a sub n minus 3, a sub n minus 5, a sub n minus 7, and it just keeps going. The top 2 rows of our Routh array we can just write down given the polynomial. The remaining rows we have to generate or construct or build. So we're going to have a B1, a B sub 2, and a B sub 3. Then below the B's we're going to have C's, C1, C sub 2, etc. So now let me tell you how you build or create that B sub 1 coefficient. And it's similar, I shouldn't even say this, it's similar to a determinant, but it's not quite the determinant, it's kind of backwards. To build B sub 1, we start with we always use this, well, to build the B row, we use the 2 rows above it. To build the C row, we use the 2 rows above it, the B and the B and an A row. Now, we're always going to be using these 2 entries or these 2 entries depending on which row we're on. But for B1, we're simply using the 2 rows above, leftmost column, and then we jump over a column to the right from B1 and use those elements. And B1 is going to be a sub n minus 1 times a sub n minus 2 minus a sub n times a sub n minus 3, all divided by a sub n minus 1. I'll write that down. B1 is now a sub n minus 1 times a sub n minus 2 minus a sub n times a sub n minus 3 all over a sub n minus 1. There's a pattern there. A sub n minus 1 times a sub n minus 2 minus a sub n times a sub n minus 3 divided by a sub n minus 1. What's b sub 2? B sub 2, again, we use these two entries, but now since B sub 2 is in the second column, it now needs to use the column to its right. Meaning, we now create B sub 2 by taking A sub n minus 1 and multiplying that by A sub n minus 4. Then we subtract A sub n times A sub n minus 5 and divide by A sub n minus 1. So B sub 2, if I am doing this right, is A sub n minus 1, if I'm keeping track of my subscripts, times A sub n minus 4, minus A sub n times A sub n minus 5, all over A sub n minus 1. Is that clear? Just for completeness, what's B sub 3? So now we're using the A sub n and the A sub n minus 1 always, but now we go one column to the right of B sub 3. We're using this B sub n minus 6 and A sub n minus 7 column, 2 rows above us. Is that clear? And building it up the same way. We now have B sub 3 is A sub n minus 1 times A sub n minus 6 minus A sub n minus 7 all over A sub n minus 1. That's the B row. Now, to generate the C row, it's the same process, except it's now using the 2 rows immediately above it. C1 is now going to use B1 times A sub n minus 3 minus A sub n minus 1 times B sub 2, all divided by B1. Is that clear? C1 is now B1 times A sub n minus 3 minus A sub n minus 1 times B sub 2 all over B sub 1. C sub 2. Now we use the column to its right, but we still keep using the leftmost column. So that's B1 and B sub 2 that we will know. B sub 1 and A sub n minus 1. Then we have B sub 1 times, what are we going to use to create B sub, or C sub 2? B1 times A sub n minus 5. We're using the column to the right of C sub 2. So that's now times A sub n minus 5 minus A sub n minus 1 times B sub 3 all over B1. And we just keep going and going. Is that making sense? Now, what we want to do is have about 20 more minutes. All right, let's look at an example. Since you guys have 20 minutes, and I know that the class coming in is going to be patient and not come in for another 20 minutes, what happens for the general second-order polynomial? Meaning, what if delta of s is equal to s squared plus a1s plus a sub 0? We want to perform the Routh-Hurwitz criterion, or apply that. What's the Hurwitz test tell us? Now assume that A1 and A sub 0 are positive. Hurwitz says present and positive, right? So it passes the Hurwitz test, and now we have to keep going. I will release you, but I'll fill in the Routh array. You now try to do the Routh array on your own and see if it checks, and we'll actually verify using the Routh array that the Hurwitz test for a second order is necessary and sufficient. And this is what you could have used on the very first problem that we gave you to begin the lecture.